Good morning, friends. Today I am going to start some other kind of examples for this contour integration. We have already discussed the notion of complex integration and of residue at a point. We now proceed to the evaluations of real definite integrals with the help of contour integration and the theorem of residues. But we have to choose a proper integrand and the contour for that. So before proceeding to the evaluation of definite integrals, we have to go through some of the remarks and a new concept. First remark is, we will evaluate integral of the type minus infinity to infinity px over qx dx, where qx has no real roots, right? This thing you have to remember, it should be having no real roots. Then second thing is degree of qx is greater than equal to degree of px plus 2. That means if degree of qx is 5, then degree of px must be less than 5 or strictly less than 5, right? So degree of qx should be greater. And then is the another remark, this is very important to understand. If tau is an arc where theta is lying between theta 1 and theta 2 of the circle mod z is equal to r, if you notice here, this is your x-axis and this is the y-axis, and there is a semicircle drawn on this real axis, right? And this semicircle is the upper half, it is in the upper half of the plane, right? And this tau denotes the arc from plus r to minus r. It is a semicircle. So limit r tends to infinity on the integration over this tau fz dz is equal to iota times the difference of the angles. If the first angle is 0 degree, then the theta 2 is taken to be as pi because it is from r to minus r. This is 180 degree. Into limit z tends to infinity z into f of z. This is the formula for calculating the integration over this tau, right? This you have to remember. In particular, if tau is a semicircle of the circle mod z is equal to r, r is taken to be large in the upper half of the plane from r to minus r. Then this integration over this tau fz dz, if you take the limit r tends to infinity, this will be equal to iota. Now theta 2 is pi and theta 1 is 0, so it can be written as pi minus 0 or iota pi, right? Limit z tends to infinity z f of z. Fine? Alright. Next, I'm going to start now an example. Now we have to integrate the given integral over two things. One is over this real axis plus this arc, which is your semicircle. This complete contour is the circle C. This is C, the complete contour, right? Which consists of this real axis plus this semi-half circle, which is tau. Now we have to show that this integration minus infinity to infinity 1 over x square plus 1 dx is equal to pi. We will integrate fz equal to 1 over z square plus 1 along this C. What is C? C is the contour consisting of this real axis from minus r to plus r, followed by a semicircle, this tau, from plus r to minus r. This is your complete contour, which includes the real axis plus the semicircle, right? Now why I have written here f of z equal to 1 over z square plus 1? Because z is x plus iota y, where x and y both the coordinates are including, right? But we need to show that this is from this integration for 1 over x square plus 1, which is for the real axis. So to start, we have to choose this contour C, and for that we have to change the function as f of z equal to 1 over z square plus 1. We have to integrate this function first, right? Just replace x with your z. Now what are the poles of fz? What is fz? It is 1 over z square plus 1. What are the poles? Taking the denominator 0, poles are z equal to plus minus iota. Very good. Now the poles are z equal to plus minus iota. Which of the pole lie inside the circle? Of course, z equal to plus iota lies inside the circle and minus iota lies outside the circle. So we have to calculate the residue for this pole z equal to iota which lies inside the circle. Now the poles of fz is z equal to, alright, poles of fz are plus minus iota, of which z equal to iota lies inside the circle or inside C, right? Now the residue of this fz at iota, this is equal to, the formula is for calculating the residue, limit z tends to iota, z minus iota, the function is 1 over z square plus 1. Can I write it as z plus iota and z minus iota? This cancel and this will be, putting z equal to iota over here, I get 1 over 2 iota. Is it fine? Alright. Now by Cauchy residue theorem, this integration over C fz dz is equal to 2 pi iota times the sum of the residues. Because I'm having only one pole over here, so I have to write only the residue for that pole. So this is 2 pi iota 1 over 2 iota, which is iota iota 2 cancel, which is pi only, right? Now this circle, the contour C, that is this integration over C fz dz, this has to be written in the next step as, this is, we have taken a contour from minus r to plus r over the real axis, and the real axis is our x coordinate. So we have to write this in x. This is x square plus 1 dx plus, and also through this tau, right? So the integration over C is from this real axis plus the integration over this tau. So over this tau, for the tau I have to write it as z square plus 1 because x and y both the coordinates are including, as z equal to x plus iota y. This is your pi. Now we have to calculate this. The formula, the first remark, that integration over this tau 1 over z square plus 1 dz is equal to iota pi minus 0 limit z tends to infinity z into f of z. So let's find out. This is iota pi limit z tends to infinity z f of z is z square plus 1. If you take this limit z tends to infinity over here, cancel your first z with the denominator and this will be z plus 1 over z square. So this is actually comes out to be 0, right? If you solve, this is 0. Now putting this value over here, and also because we need in the given integral minus infinity to infinity, so I have to take this r very, very large. So let's take the limit r tends to infinity on this one. So this is let r tends to infinity on 1. So this is limit r tends to infinity one over x squared plus 1 dx. This is 0, which is equal to pi, which implies, can I write simply as minus infinity to plus infinity? So this is equal to pi, erasing this 0 also. This is pi, which is the required condition, which is a required thing needed to prove, right? This we have to prove. It is now proved. Next, prove that integration from 0 to infinity 1 over x squared plus 1 whole square dz is equal to pi by 4. Now here the integration is from 0 to infinity, not from minus infinity to infinity. But we have to go through our proof with the similar steps what we have done in this example, the previous example. So let's start. We will integrate again f of z equal to 1 over z square plus 1 whole square along the c. And the poles of fz, this is taking denominator equal to 0, which is z equal to plus minus iota. I'm having simple poles or double poles? Yes, the poles are double poles because here the power is 2. So clearly the poles of fz are plus minus iota, of which z equal to iota lies inside C of order 2, or it is your double pole of order 2. Now finding the residue for this, because it is z equal to iota of order 2, the formula for that is 1 over k minus 1 factorial. K is 2 here, so this is 1 over 2 minus 1 factorial. Limit z tends to infinity, z tends to I. Z tends to iota. D by dz, we have to derivate this. How many times? K minus 1 times. That is only once. Z minus iota, the power k. K is 2 here, into f of z. So this is equal to, this is 1. Limit z tends to iota. D by dz of z minus iota whole square. Now this is f of z, 1 over z square plus 1 whole square. I am writing in factorized form. This is z plus iota whole square and z minus iota whole square. So this is cancelled with this, and we will be getting, I am having space. So this is limit z tends to iota d by dz of 1 over z plus iota whole square. You have to derivate this once. So this is equal to limit z tends to iota, the differentiation is minus 2 over z plus iota whole cube. And when you put z equal to iota over here, you get 1 over 4 iota. Right? Now by Cauchy residue theorem, this integral over c fz dz is equal to 2 pi iota times the residue. And the residue is 1 over 4 iota, which is equal to pi by 2. Now this integration is actually from minus r to r fx dx plus this semicircle tau fz dz, which is pi by 2. So I have to calculate this first. So this is equal to, I know the formula for this, iota pi minus 0 limit z tends to infinity, z over z square plus 1 whole square, z into f of z. So f of z is 1 over z square plus 1 whole square. So take this z the power 4 z square common, cancel that z with the numerator. You will be getting pi iota limit z tends to, okay, I write in the bottom. So you will be getting, oh my god. Okay, so this is equal to pi iota limit z tends to infinity 1 over z cube over 1 plus 1 over z square whole square. This comes out to be, because it is infinity, so this is 0. So you will notice that every time this integral over this tau comes out to be 0, right? So put this value over here, and also you have to take r tends to infinity. So let r tends to infinity in 1, this will be minus infinity to infinity 1 over x square plus 1 whole square dx, which is pi by 2. Now is this function even or odd? Because in the given integration I need 0 over here. So this function is, of course, it is an even function. So whenever your function is even, this integration is changed into twice 0 to infinity 1 over x square plus 1 whole square dx is equal to pi by 2. Taking this 2 to the other side, this is 0 to infinity 1 over x square plus 1 whole square dx is equal to pi by 4. This is the required integration we needed to prove. Hence the result. Alright guys, next time we are going to solve some more examples of the other kinds also. Right, alright. If anybody needs my course of real analysis or vector calculus, the coupon for these courses are provided in the description box. If anyone needs to enroll that course, you can check the description box and you can enroll that course via that coupon codes which are provided. Thank you so much guys. Goodbye. Have a very nice and blessed day.